Hello all, welcome to my channel. Um, I'm back with a new video, and in this video we will be discussing what iceberg is and why it is so much in discussions around in around data engineering circle. So let's get started. So first thing first, iceberg is an table format, and to know what does a table format mean is let's see where the table format fits into the whole ecosystem as of now. So we generally have in storage layer on which we can have S3, ADLS, GCS, SDFS, Mini IO, Ozone. So there are multiple implementations of object storage. On top of that, on the in the object storage we store file formats like for example Abro, Parquet, ORC, Vortex, Lance. So there are different file formats which are present. And on top of that, we have a concept of table. So what this table format does, it whatever data that we have stored in the files, in the form of files on particular object storage location or any storage location, it creates a table out of it, or it behaves, it makes that data presentable to the system which is consuming this. For example, let's say Sparkling or Presto, if they are trying to consume these files from Iceberg, so they will see that as a table rather than saying that as a particular list of files. So, for example, let's say to and why this is needed. Let's take an example that I have a daily data that I insert into my table, insert into my some processing I want to do, and I receive daily data on a daily basis. So let's say the part one of the initial phase of that my pipeline is to load the data into a system. So what I can do, let's say if I just want to have multiple files, I can keep daily files, and then I can ask my Spark job to just load the data in a format and load whole the data, all the files, and then do the processing. So that is one approach. But the other, that in that approach, what will happen that every time I have to read the whole data because there is no uh, structure or no format defined on top of it. But if we use Iceberg or any other table format, there are other table formats as well. Hoodie, Delta is also there. So I'm just taking example of Iceberg because that's the point of interest of this video. So what Iceberg provides is on top of those files, it will expose an API which behaves like a table. So when Spark or Flink or Presto or any compute engine connects to these files, so they don't have to first of all load all the files. So that what files will be scanned is decided by Iceberg itself. So Iceberg tells, okay, if you want to read, let's say I say select star from but that particular table, and then we say whatever is partition is X, Y, Z. So that based on the layout, it will simply go ahead and only allow ask the Spark to read X number of files instead of using the reading the whole file. So this is why a table format is important. And if you say table format is nothing but a way to organize their files, and they try to bring database like features to data lake. So the evolution of table format, how it has happened is first it was a relational table format, then it went to directory oriented table format, then log oriented table format, and now today we have unified open table formats like Iceberg. For example, Hive, Apache Hive was one of the earliest and most used table formats because this also gave Hive stores data in uh, SDFS location. It has a meta store which stores the metadata about the storage, and then when we query, the request first goes to the meta store service, and then it says, okay, go ahead and read these files for your data. So this is, if you see the hierarchy of Hive table format was like first it will be having DB, a database one, table two. Each table will have certain partitions. Each partition will have certain data files. So if we want to only read this particular partition, we say select star from db.table where partition is equal to partition one, and only these files will be read. If we say partition two, then the files related to partition two will be read. So that way we make it more easy to consume those files which are out there in the market. So this is all about that. So coming back to here, what features that or slight history of the uh, Iceberg ecosystem itself. So Iceberg was created in 2018 at Netflix. Then it was open sourced in 2019. Netflix was building. Netflix built this because they had a lot of S3 data that they want to run analytics on top of it. So they created this Iceberg table format, and then they open sourced in 2019, and in 2020 it was given up for incubation in Apache community, and then it became a top level project in 2021. 2024 was kind of it became the standard for the data lakes, and 2025 we have the V3 version of this that supports streaming as well. So this is the overall journey of Iceberg as of now. The features that Iceberg supports is ACID transaction because it follows snapshot isolations. Iceberg ensures ACID for data lake transaction. Schema evaluation, so we can have multiple schemas in, let's say in the future, previous partitions we can't have. Let's say we didn't have something. If we want to add a new column, we want to remove a certain column, that schema evaluation support is there without disrupting the existing pipelines. Then we have support of partition evaluation, like today we can add and remove partitions without modifying the whole data. Then timetable and rollbacks are possible because we have snapshots, and then using snapshots we can go back in time. Hidden partitioning is there, so this means that we don't have to do an explicit partitioning as a physical layer to improve the query. It can handle certain hidden, like for example, uh, producing partition values on a row based on a row of a table. So that is something which is interesting. We will discuss more about this in upcoming videos, how hidden patterning works in Iceberg. We have optimized query performance because it uses metadata indexing, and then Apache Iceberg accelerates the NLQ queries because it simply skips unnecessary data that needs to be scanned. This is the very, I will say the most important, no, one of the most important features, that it supports multiple engines. So this means that we don't have to create multiple copies of the same data to be consumed from different engines. For example, uh, if we are using, if we were if we wanted to do analysis both in Spark and Presto, so the data first needs to be loaded in Presto as well. Spark will read from, let's say, data lake. So there will be two copies of the same data. In here, if both the engines understand Iceberg, so the same data can be read by Spark with its own schema, while Presto reads it with its own schema and catalog. So that's how it supports multiple engines. Snapshot isolation, this is like uh, that whatever changes we are making does not affect the older version. So that's how the snapshot isolation works. Atomic commits, that means that either the whole, but let's say we are making a delete operation, either the whole delete operation succeeds or it doesn't succeed at all. So that's how the atomic nature of this is. Partial, there is no partial commits happening. And every transaction on Iceberg creates a new snapshot. That means we can go back in time if needed. Uh, so this let's say this is an architectural view of Iceberg. So at high level, we have three layers in Iceberg table. Um, Not table, Iceberg system, I will say. One is the catalog layer, where we will have a catalog which stores the metadata pointers. And this metadata pointer is nothing but a pointer to the metadata file snapshots, which are stored in the metadata layer. So this metadata layer contains majorly three types of files. So snapshots, manifest list, and the manifest file. And this each manifest file points to multiple data files, and that becomes the data layer. So this is how the files are organized, like for a particular table. We will see how those are mapped as well. So catalog is simply the metadata pointer. It can be Hive, Nessie, Glue, LakeFS, REST catalog, DynamoDB, Glue. Then we have a newer catalog like Unity catalog is also supported, Polaris. So there are multiple catalogs that we can choose. And so this we have metadata layer and data layer for this. And if we see the same image, if we enlarge, so means the previous image that we were saying, if we enlarge it, this will be the picture that will be coming, like something similar. Is that the snapshot file is this. So each snapshot file points to certain manifest list. The manifest list points to certain manifests, and those manifests point to data files. And if you see in the folder structure how it is there, so let's say you have a table, so table, then you will have a metadata folder. Under inside that you will have v1.metadata.json, v2.metadata.json, then snapshot, then you have avro manifest file and manifest list. And then inside the data folder, based on the partitioning scheme, you will have .parquet file or whatever file format that you choose. But Parquet is the most common one, and partition directories and files will be present in this. So this is the architecture of Iceberg, how it stores that. And inside this metadata JSON file, it stores the snapshot information, schema, partition specs, and sorting orders. The command in the manifest file, it stores the file path, which partition data, file format, record count, file size in bytes, value counts, null value counts. So there's some metadata, lower bound range, upper bound range about the manifest. So everything is stored in here. Manifest list contains the manifest path, then it contains the location, which is the length of the bytes content, like where this 0 is equal to data and 1 is equal to delete. So that is there. Partition array of something as array summaries and nullable, non-nullable, upper, lower ranges. So those things are also stored. And data file is the actual file where actual physical file where the data is stored. We have delete files. So delete files is to track if we delete any operation, the files are not rewritten. Uh, in case we have merge on read tables, it simply adds a new files which says that okay, when you are trying to read a table's data, read this file and remove the rows which are mentioned in this particular delete files. um, we have puffin files as well, which is nothing but a new format to track binary blobs, and in this we store the deletion vectors as well. This is similar to a delete file, but that is stored in a bitmap vector. And the partition stat file, which stores the information stats about the partition. uh, the different file types which are present. For example, data files is named under .parquet, manifest file is with .avro, snapshot file is again with .avro, metadata file is .json, version hint file is on txt, puffin files, there are some other files. And how write happens. So when this is interesting to know how a write operation happens in Iceberg, is that the writer will visit the catalog to get the current metadata file location. It will look at the current metadata, then it reads the metadata file to understand the table's current schema and partition scheme to prepare for the later data writing. So let's say it says, okay, I have to write to a new partition. So the writer writes new data files following the partition scheme. The writer creates the manifest file in Avro format. The manifest file contains the data file location plus the file's stats. So first the data file will be written, then it will create a manifest file that will be written, then it will create another manifest list which will have the previous manifest with the current manifest as well, saying that okay, this is the this file contains the manifest file location for the newer data that has been added, number of file rows and everything will be mentioned in this manifest list. Then the writer will create a new metadata file which will point with the latest snapshot of all the previous snapshots, and then it will say that this file will have the table's base location, manifest list, the new list that was created, snapshot ID, sequence number, updated timestamp, everything, and then this writer will just swap the snapshot to the new latest snapshot and make the current pointer point to the current metadata that was created. So in a flow wise, if you see, read current state, means it will scan and read the current state. Then it will do write the data file. Written data file is written here. It will then read the metadata layer information, determine the base metadata. It will read this from here. Then it will check for data conflict. If it is there is no conflict, then it will go and write the metadata files, which is again manifest list. If and then do the commit. If commit fails, it will again be retried. But if no commit is successful, then it will go to Iceberg catalog, get a success, and then the transaction gets completed. And that's how it maintains a seed and other properties that are needed. So this is for the write path. The read path, how it happens is the reader first visits the catalog to find the table's current metadata. It will get that current metadata. The reader will collect the table's schema to check how the data is organized. The reader retrieves the current snapshot, and then it will using that snapshot, it will read the locate the manifest list. Using that manifest list, it will find all the manifest files. Using those manifest files, it will have the information of partition column of each of the manifest file, and whatever is being asked in the query, based on that, it will remove certain manifests. Then reader will open each of the data file mentioned in the manifest list, which is which meets the criteria of the query, and then each individual file will be read. and then that individual file, data file, after reading it, it will collect the information, and then whatever it has to do, it will do the processing. So that's how the read happens in Iceberg. Uh, uh, so one thing that it Apache Iceberg supports is this partition and schema evolution, which we have already touched upon a little bit, but let's say simply in schema. So what this means is that partition evolution will allow us to add and remove partitions without the whole rewrite. Schema also means that earlier, means let's say instead of rewriting the whole table, if we want to add a new column or add a new change at a column data type, we don't have to do that. Schema evolution will take care, and if we enable schema on merge, it will automatically do that as well. So, and hidden partitioning. So what happens is, based on the transform value, so there is a concept of transformation which can be tracked at the metadata level. So based on that, so those transformations, we can have hidden partitioning that allows us to not have physical partitioning, and help us make Iceberg slightly more customizable in that sense, and more reusable across different engines. Versioning and time travel, this is something which says, because we have snapshots of different timestamp for a particular table. If we want to go back in time, we can simply look at that particular version and then say that give me the records as of this version. So each snapshot will have its own metadata pointer, which files are there, which files where has to be referenced. So everything is there, and simply we can go and get the older data that we want to see. So that's how Iceberg works, and Iceberg is able to deliver performance at an higher level. This is one example, like what file formats are present, how Iceberg support is there, table versioning, catalog level versioning, read write paths. So this we discussed already, that how it is the write path. Uh, in the read path, we already discussed what happens in there. So yeah, this was it for now. Uh, if you like it, do share and have a nice day.